So, welcome students. This is part 2 of the entrance exam questions that I'm working out. So here I'm working out 14 questions. So let's get into the first one. The apparent flattening of the sun at sunset and sunrise is due to, polarization. Polarization is where you cut out certain planes of vibration. Because light originally vibrates in planes perpendicular to the direction of propagation. In polarization, you cut out all of those planes of vibration except one. That would be plane polarization. So this flattening of the sun has nothing to do with polarization. What is interference? Interference is when you have two coherent sources, and light from the two sources are superimposed on each other, and that produces dark and bright bands on a screen. Now, this one doesn't have anything to do with interference. Total internal reflection. In total internal reflection, whenever light is passing from a more denser medium to a rarer medium, which means from water into air, as an example, and if the angle of incidence is greater than the critical angle, then the light will return to the denser medium. So instead of going into the second medium, it'll come back into the first medium. That is total internal reflection. That is not connected to this. Diffraction or diffraction, whatever way you want to call it, is the bending of light around the edges of obstacles. So that is not the answer either. So that means the answer is refraction. Let me explain. Now, during sunset and sunrise, the sun is a long way off from the earth, right? It's a long way off. So light has to travel a longer distance before it reaches the eye. Now, from the top and bottom of the sun, when light reaches the eye, they go through different amounts of bending because the angles of incidence are not the same. Let's see from this diagram. So this unequal bending of light coming from the top of the sun and the bottom of the sun, because it bends unequally, it tends to flatten the sun, you see? So that's why the sun appears to be flattened at sunset and at sunrise. So that's the actual answer. So the reason is refraction. And this diagram should show that clearly. Let me just move this up. So light coming from the top and from the bottom of the sun, they bend differently. So you see that this appears to come from here, while this appears to come from here. And this distance is not exactly the same as the diameter of the sun. So it appears to be smaller or flattened. That's the answer to that question. Moving on to the next one. This one says, the polarizing angle for a medium is found to be 60 degrees. What is the critical angle of the medium? So number one, we have to know what polarizing angle is. Polarizing angle is the angle of incidence for which maximum polarization is produced. Again, polarizing angle is the angle of incidence for which maximum polarization is produced. And then you have to know what is called Brewster's law. According to Brewster's law, tangent of the polarizing angle is equal to the refractive index. So let me write that. So the refractive index, mu, is equal to tangent of the polarizing angle, theta. And when we deal with critical angle, and when we apply Snell's law, we also get this formula, mu is equal to 1 by sine c, where c is the critical angle. So now we can use these two formulas to find out the value of the critical angle. You know that tan can be written as sine theta by cosine theta, right? So, or in this case, it's actually given. So polarizing angle is given as 60 degrees. So since the angle of a polarization or the polarizing angle is given as 60 degrees, we can use mu is equal to tan 60 to find mu. Well, what is tan 60? How do you get that without a calculator? Tan 60 is sine 60 by cosine 60, which is root 3 over 2 divided by 1 by 2. Because cosine 60 is 1 by 2, which is root 3 over 2 multiplied by 2 by 1. Or simply remember that tan 60 is square root of 3. So once we know that mu is square root of 3, now we can use it in this formula. You put the value of mu as square root 3 is equal to 1 by sine c. Make sine c the subject, which gives 1 by root 3. And so C is sine inverse 1 by root 3. So that is the answer to this question. All right. 17. Identify the mismatch in the following. So there is a mismatch. Okay, let's look at each one. Myopia. Myopia is short-sightedness. You know, short-sightedness is corrected using a concave lens. Now, what is short-sightedness? Where a person is able to see things that are close by clearly, but beyond a certain distance, the person can't see it. Well, I am suffering from myopia, so I am the best example. That's why I have concave lenses. So myopia or short-sightedness is corrected using concave lens, so that's correct. Now, rear view mirrors. Rear view mirrors, you see those side view mirrors in an automobile, they are not concave mirrors. They are convex mirrors. So that's wrong. So rear view mirrors are not concave, but instead they are convex. What is the reason? Because convex mirrors produce an upright image, which is really small. So in the rear view mirror, you want to see a smaller view of the vehicles that are approaching from behind, right? So that is possible only with a convex mirror. With a concave, you would see a magnified, sometimes inverted image. You don't want that. You would be scared to death. So that's wrong. Rear view mirrors are convex mirrors. C, hypermetropia. That is far-sightedness. Some call it long sight, and that is corrected using a convex lens. So that's right. Astigmatism. Astigmatism, is where you have horizontal, that's vertical, and horizontal bars. And you look at them, for some people, they're able to clearly focus on one of them, like the vertical ones may be clearly focused while the horizontal ones are blurred, or maybe the other way. So this is astigmatism, and this is because the angle of the lens is twisted, and that is corrected using a cylindrical lens. Astigmatism is corrected using a cylindrical lens, so that's correct. Now, reflecting telescopes, they do use a concave mirror. Reflecting telescopes, the objective of the reflecting telescope. A telescope has an objective and an eyepiece. The objective could be either a convex lens or it could be a concave mirror. So we found the mismatch. B and E have been mismatched. So if you correct them, you will get this. Reflecting telescopes use a concave mirror, and rear view mirrors are convex mirrors. All right, so that is how you answer this question. I've written down a few points that I've told you. A concave mirror is an objective. It's able to produce a real image, while a convex mirror produces a virtual image all the time. And like I told you, the images are smaller and they're always upright. Okay, because you want to see upright images while you're driving, not inverted images, because that'll scare you to death. So that's how you answer that. And then you have 18. And then you have 18. In Young's double slit experiment, to increase the fringe width, okay, So you have to do all those things. Which one is correct? Now you need to know the formula for fringe width. In a double slit experiment, you have those two slits that are separated by a distance, and then in front you have a screen, and that's another distance from the slits to the screen. So there are two distances there. One is the distance between the two slits. The other is the distance of the screen from the slits. Are you with me? And then behind the slits you keep a source, right? Let me show you the diagram. So behind the slits you have a source, and this distance doesn't matter. So how far you keep the source behind the slits does not matter. So that means B is wrong, because that talks about the source being moved towards the slit. And then C is again talking about the source being moved away from the slit, okay? So that distance doesn't matter, so B and C both are wrong. And then here is the formula for fringe width. Beta is the fringe width. It's given by lambda caps D by small d. So there are three ways of increasing the fringe width. Increase the wavelength, which means use red light instead of blue. Increase the distance between the slits and the screen, that's caps D. Decrease the distance between the slits, that's small d. So if you look at D, it says the slit separation is increased. If you increase it, beta is going to decrease. So that's wrong. Then E says the screen is moved towards the slit. So what are you doing to caps D? You're decreasing it. Again, when you decrease that, beta decreases. So that's why D and E are wrong. So that leaves us with A. The wavelength of the source is increased. Now remember, students, that I could give you the answer straight away in 5 seconds, but I'm also trying to explain why the other choices are not correct. Okay? So you get a complete understanding of the answer and how we arrived at the answer. 819. Light of wavelength 5000 angstrom units is incident normally on a slit of width 2.5 times 10 to the negative 4 centimeter. The angular position of the second minimum from the central maximum. So what topic is this? What do you think? Is it interference? No, it's not. Because light is incident on one slit. This is diffraction at a single slit. This is diffraction. So when you read the question, first get to the topic, and then think about it, right? And you're asked to find the angle. You're given the wavelength lambda, you're given the slit width, you're asked to find the angle of the second minimum. Second minimum. So now we need the condition for minimum or darkness. The condition for minimum or darkness for a single slit is d sine theta is equal to m lambda. So when you rearrange, you get theta is sine inverse m lambda by d. Now what are the terms? M is the order of the spectrum. So here it says second minimum. So m is equal to 2. Lambda is the wavelength, and wavelength has to be in meters, not angstrom units. And d, caps D, is the width of the slit, and that has to be in meters. So we have to change angstrom units into meter and centimeter also into meter. You need to know 1 angstrom unit is 10 to the negative 10 meter, right? So sine inverse 2 times lambda. So lambda is 5000 angstrom units. That would be 5000 times 10 to the negative 10 meter divided by, you got to change that into meters, so it's 2.5 times 10 to the negative 6 meter. So now we can just cross out the powers, look at it carefully, and you can see that you're going to get 2 by 5 for sure. So question number 20. An electron of mass me and a proton of mass m sub b are accelerated through the same potential. Then the ratio of the de Broglie wavelength. So now it's about de Broglie wavelength. So, de Broglie waves are matter waves, and they have an associated wavelength that's given by lambda is equal to h by momentum. momentum is m times v, right? So that's the formula for de Broglie wavelength. H is Planck's constant, m is the mass, and v is the velocity. In this question, there is no mention about the velocity. Instead, the potential through which the electron and proton are accelerated is given. So now we have to be able to connect the velocity to the potential. And we do that by knowing that the work done by the potential is equal to the kinetic energy. Okay, the work done by the potential becomes the kinetic energy. And the formula for work in electrostatics is charge multiplied by voltage. So that's the work done. And you know, kinetic energy is 1/2 times mass times velocity squared. So once we know this, we are trying to substitute for velocity. So what I do is I square both sides. Actually, I brought the 2, 1 by 2, the 2 to the left side, and then I also multiplied both sides with the mass. You will see what I'm trying to do. And because I got this now, if I take the square root on the right side, I'm going to get mv, correct? And on the left side, of course, it will become square root 2 mev is equal to mv. Now I got the formula for momentum, so I can plug that in here. So I would get lambda is equal to h by square root 2 mev. With that formula, now we can work this out. So the de Broglie wavelength of the electron divided by that of the proton would be simply dividing this, right? Dividing that twice, and then the common terms will get cancelled. H is a constant, and E is the charge, which is the same for an electron and a proton. Yeah, one is negative, the other is positive, but the values are the same. And then they are both accelerated through the same potential. So V also, voltage, will get cancelled. And of course, 2 gets cancelled. So that leaves us with what? 1 by square root of mass. Remember, mass is in the denominator. That's why when I took the ratio, it's mass of the proton in the numerator divided by mass of the electron. You see the inverse ratio come up there? That's because it's 1 by. So remember that. And there is the square root. So that's what you get, and that is the answer, okay? So E is the answer. I hope you got that. Number 21. This is to deal with radioactivity. The half-life of a radioactive substance is 20 minutes. What do you mean by half-life? Half-life is the time taken for half the number of radioactive atoms to decay. So if you start with 100 radioactive atoms, the time it takes to become 50 is called the half-life. Or if you take 50, the time for it to become 25 is called the half-life. So whatever is the case, half-life is the time taken for it to become 50% of what you started out with. 50%. So now the question says the half-life is 20 minutes, and then the time taken between 50% decay and 87.5% decay of the substance will be. You know, we can actually do this without any formulas, but let me show you how first with the formulas. So to get to 50%, it takes 20 minutes. And then to get to 25% from there, it will take another 20 minutes. So totally, it would take 40 minutes to get to 75% decayed, right? It'll already take what? It'll already take, how many minutes did I say? 40 minutes to get to, all right? Okay, so now let's work it out using the math part. Half-life, you have to define something called lambda, and lambda here is not the wavelength, it's the radioactive decay constant. And this is the relation between radioactive decay constant and half-life. See that? Radioactive decay constant is 0.6931 by T half. And here in this case, T half is 20. So I found the radioactive decay constant. So you can do it that way. and then I get the value of lambda, and then I can plug it back into this formula. That's the formula for radioactive decay. N by N naught is e raised to minus lambda t. N naught is how many you start with. N is what remains. So when you say N by N naught, remember N is how many radioactive have remained after the decay. So when you say 87% has decayed, remember this is a very important point. 87.5% of the atoms have decayed. How many remain? Only 12.5%. You start with 100, 87.5% is gone, you remain with 12.5. So N is not how many have decayed, but N is how many are yet to decay. That's 12.5. So when I rearrange this formula, and change the exponential into natural log and all that, and then I make t the subject, and I put 1 by lambda, natural log 100 by 12.5, I get 59.92 minutes. So it takes about 60 minutes to get to 87.5% of the decay. So 50%, it takes 20 minutes, and then it takes 60 minutes. And so the difference is 40 minutes. We could have done this without any math. Why? Because can A be the answer? No. Can D be the answer? No. Why? I told you. To get to 50%, it takes 20 minutes. And to go from 50 to 75, it'll take another 20 minutes, isn't it? Yeah. So that's already 40 minutes to get to 75%. See that? So that's where if you get 75, you already took 40 minutes. And this is to get to 87.5, so it has to take more than 40 minutes. You know what I'm trying to say? So it has to be more than 40 minutes, and so 40 minus 20 is 25. It cannot be 25, never can be 10 minutes. It cannot be 30. So just logic will show you that the answer is 40 minutes. So you need not do all this here. I hope you're able to understand what I said. All right, let me try that again. To go from 100% to 50%, it already takes 20 minutes. To go from 50% to 25%, it'll take another 20 minutes. So to go from 100 to 25%, 100 to 25%, you've taken 40 minutes. See that? You've already taken 40 minutes. So the answer cannot be less than 40 is what I'm trying to say. The ratio of the surface area of the nuclei, these two nuclei are given, and tellurium, I think, and aluminum, what's important is the mass numbers, because the surface area or the volume of a nucleus depends on its mass number, which are these two numbers, 125 and 27. And then here are the two formulas you have to remember. The formula for the radius of the nucleus is R naught A raised to 1 by 3, where R naught is a constant. It's 1.2 times 10 to the negative 15 meter. That's the R naught. That's okay. And then A is the mass number. Now, surface area, you imagine that the nucleus is a sphere. And the surface area of a sphere is given by 4 pi r squared. So the surface area of the first one would be 4 pi r1 squared. And second one, similarly, would be 4 pi r2 squared, right? But then now you have to substitute for r1 and r2, or take the ratio. S1 by S2 is going to be surely r1 squared by r2 squared. But remember, r is given by this, so when I substitute and then divide, I know that r naught will get cancelled, and a will become a raised to 2 by 3. Why 2 by 3? Because you're squaring this. A raised to 1 by 3 squared is a raised to 2 by 3. Simple, right? A raised to 2 by 3. So that's how I got that. And then all I have to do is A1 is 125. Okay, or you can take A1 by A2 whole raised to 2 by 3. You can do it that way too. So A1 by A2 whole raised to 2 by 3. So 125 is A1, A2 is 27. And then this means that you have to calculate in your head, quite simple, because raised to 1 by 3 means cube root. What is the cube root of 25? Cube root of 125. 5. Because 5 times 5 times 5 is 125. So cube root of 125 is 5. And then you have to square it. So that'll give you 5 squared, 25. In the denominator, cube root of 27 is 3. Because 3 times 3 times 3 is 27, right? And then 3 squared is 9. So the answer is 25 by 9. That is how we get the answer to that question, 25 by 9. 23rd question, if the frequency of incident light falling on a photosensitive metal is doubled, then the kinetic energy of the emitted photoelectron is. So this is photoelectric effect, and now we need the relation between what? We need the relation between kinetic energy and the frequency of incident light. So you have to remember the photoelectric equation, which gives the kinetic energy 1/2 times mass times velocity squared is equal to the incident energy of the photon, which is h nu, minus the threshold frequency times h. So h nu naught. Nu naught is called the threshold frequency, and h times nu naught is called the work function. So work function is h nu naught. And work function is a constant for a particular metal. So in this case, the work function is constant. Now, 1/2 mv squared is kinetic energy. So that simply means kinetic energy is h nu minus work. And second case, when you double the incident frequency, you're going to get h times 2 nu minus work function. Okay, let me first show the longer method and explain it, then I'll show you a shortcut to get the answer to this. So from this one, you can make the work function the subject, which will make it h nu minus k1. And so we can now substitute into this, where you have the work function, you write this whole thing, h nu minus k1. And then what we're trying to find is how much it increased, right, as a percentage. So it'll be, we're trying to find k2 minus k1 by k1. That's what we're trying to find. So mathematically, you're going to get, I took h out common. You can see 2 nu minus nu. That is h nu. And so k2 minus k1 is h nu, right? And so k2 minus k1 divided by k1 would be h nu divided by h nu minus work function. So because k1 is h nu minus work. I know that looks a little confusing, but we're trying to look at this percentage change. And so the percentage change is actually h nu by h nu minus work function. This is surely more than double. And I'm going to put some numbers and explain it to you. It's more than double. That's more than 100%. So percentage change is more than 100%. Okay. So numbers will help you get the answer much faster than all this math. But I have to give you all the math so you could understand, right? So here is the example. So the equation that we got is something like this. 20 is equal to 50 minus 30. So 20 is the kinetic energy, 50 is the energy of the incident photon, and work function is 30. Remember, the work function is constant for a particular metal. So next time the incident photon has an energy which is double, correct? Because the frequency is doubled, 50 becomes 100. And so now the work function is the same, so it's 30. 100 minus 30 is 70. So now look at that. Look at that change. 20 became 70. So it's surely more than double. You know, how many times it becomes bigger depends on the work function, but for sure it's going to be more than double. That's why the answer is more than double in this case. Hope those numbers at the end really made sense, okay? And then we have 24. I've already given the answer there. Significant result deduced from Rutherford scattering experiment. You know the experiment? You had a gold, he had a gold foil, I must say, very thin gold foil. And then alpha particles were allowed to hit that gold foil, see? And it's like I always say, it's like throwing stones on a newspaper. If you stretch a newspaper and throw stones in it, what do you expect? You expect all the stones to go through the newspaper, make holes and go through it. Now, you never expect a stone to come right back, but that's exactly what happened. 1 out of 8,000 alpha particles came straight back. Not exactly straight back, but at a larger angle, as you can see from the diagram. So most of the alpha particles went through like that, a little bit away, and many of them went straight through, but out of 8,000 particles, there is one that would do this. See that? That's called the large angle scattering of alpha particles, because that's the angle of scattering. Rutherford could only explain this by assuming that all the positive charge in the atom is confined to a small space, which he called the nucleus. And how is he able to explain that? Because the nucleus is so small, there is only a small chance of an alpha particle coming straight at it. So whenever the alpha particle comes straight at it, it's going to do the large angle scattering. But the chances are less, so most of the particles will go up, down, up, or straight through. But 1 out of 8,000 has a chance of coming straight at the nucleus, so that's why there's large angle scattering. Remember that that's how the nuclear atom model was born. The one before this, as you may know, is called Thomson's atom model, where all the positive charge was imagined by J.J. Thomson to be spread out in the atom. So this changed it. Instead of being spread out, Rutherford said all the positive charge is like in a very small region at the center of the atom. Do you know the comparative sizes of the atom and the nucleus? It's about 1 by 10,000. So I always say if the atom is as big as a football field, imagine, then the nucleus is only as big as the head of a pin kept at the center of that field. So that's the comparative size of the atom and the nucleus. All right, remember that going forward. So that's the large angle scattering of alpha particles. So that is done. And then we have 25. On an average, the number of neutrons and the energy of a neutron released per fission of a uranium atom are respectively so many bunch of numbers. So this is information that you really need to know. But it's talking about fission. It's talking about the fission of a uranium atom. Now, uranium, you could have 238, which is the naturally occurring uranium, or you have the fissile uranium, where fission can be done much more easily. That's uranium-235. So you have both of those. So it's not clear what it's talking about. That's why it's talking about the average. But generally, you know, when you have fission of uranium, you get 3 neutrons. On the average, you get 2.5. 2.5. And then each one of those neutrons would have an energy of 2 mega electron volts. So that is the answer. You simply have to remember. I just wrote this down to show you the, let me write it for 235 rather. So uranium-92-235, when bombarded with a neutron, produces barium and krypton. See that? That's barium and krypton, plus 3 neutrons, plus 200 mega electron volts. Of course, the atomic masses must add up. If you add these two, you must get 200. If you add these 3, you must get 236. Remember, there is 3 here, okay? So don't forget that. So when you take this as 3, plus 94 plus 139 should give you 236. Same thing here, 92 plus 0 is 92, and 56 plus 36 is also 92. So that's a nuclear reaction. So this is general information that you have to remember, which means you need to read a lot about fission of uranium-235, 238, and also probably read about alpha, beta, gamma emission and all that stuff. Okay. 26. Oh, I love this. These are logic gates. Logic gates. I hope you have studied about logic gates. You have the AND gate, you have the OR gate, and you have the NOT gate. 3 basic, right? I hope you know all this. And there are truth tables connected to this. And you also can combine gates. So what you see here, you see this, when you see a circle here, there, that means it's a NOT gate. And this is an OR gate with a NOT gate. So it's called a NOR gate. NOR gate. And this is simply an AND gate. So you have a NOR gate and an AND gate. And the question says, what should be the inputs A, B, C, so you get 1 here, right? 1. It's either 0 or 1. You know, it's a binary system. And then let me show you the truth tables for this. So that is a NOR gate, and then down below you have an AND gate, and I'll give you the truth tables of both. So for a NOR gate, I'm giving the truth table with 2 inputs, right? A and B are the inputs, Y is the output, and so there it's coming up. So first you have this combination 0, 0, 0, 1, 1, 0, and 1, 1. And look at this. This is called the NOR gate because it's clear that the output is 1 when neither A or B are 1. So that's how you remember. It's a NOR. So the output is 1 when neither A nor B are 1. And this is an AND gate. So before the truth table comes up, how do you say that? The output is 1 only when A and B are 1. The output is 1 only when A and B are 1. That's why it's called an AND gate. So here is the truth table for that. All right, so there you see. So now it's very clear that to get an output here, right, to get an output there, you need to have a 0 and a 0 here. Why? Because a 0 and 0 will give you 1 here, correct? Look at that, 0 and 0 gives 1. So you get a 1 here, and if you give a 1 here, because this is an AND gate, when it gets 1 and 1, it's going to give you 1. See that? 1 and 1 gives 1. That means the inputs are 0, 0, and 1. So you got to do some more reading on logic gates and get the idea of this. Okay. 27. The collector resistance and the input resistance of a common emitter amplifier are respectively 10 kilo ohms and 2 kilo ohms. If beta of the transistor is 49, what is the voltage gain of the amplifier? First of all, you have to know CE. You have to know that amplifiers need 2 for an input and 2 terminals for the output. So totally you need 4 terminals. 2 for the input, 2 for the output. But transistors only have 3. What are they? Emitter, base, and collector. So you need 4. Transistors only have 3, which means you have to use one of them as common. So you can either use the base, the emitter, or the collector as a common terminal between the input and output. In this case, it is the CE amplifier. That means the emitter is common. Or the input will be taken between the base and emitter, as I'm going to show you. The input will be taken between the base and emitter. The output will be taken between the collector and emitter. And I'll show that diagram in a second. But voltage gain is current gain times R out by R in. That's the, see, beta is the current gain. Beta is called current gain. It's anyway, I'll tell you, it's delta IC by delta IB in this case, because the output current is the collector current, the input current is the base current. That's beta. Okay, so here is the diagram. That line is the base. Here is the emitter, and then that's the collector. So the emitter is going to be grounded here. Do you also know you could have NPN or PNP transistors? The arrow downward shows an NPN. So I'm drawing an NPN. So that's the base. And there is a resistance on the emitter. another resistance on the collector, another one on the base. Okay, let me complete this. So that's IC. How do I know it's flowing in that direction? Because you see the arrow here? That shows the emitter current. So you have to have this current coming in, and then the base current coming in. They together combine and become IE. So I'm also trying to tell you that IE is equal to IB plus IC. You got that? I'm trying to give more information than is required. IB plus IC together become IE. So remember that. Okay? So that is grounded. That's the ground that I'm showing. The emitter is grounded. It's the common. So the input is here. The output is here. Okay? And this question is easy now because you are given the input and the output and bear it. So 49 times, both are in kilo ohms, so you don't have to change in ohms. It'll cancel out. So 245 is the voltage gain. That's why it's called an amplifier. What does that mean? That means if you give 1 millivolt here, 1 millivolt, you're going to get 245 millivolts on the output. That's how when a little man like me speaks into an amplifier, you hear a big booming voice because it makes it 245 times bigger, okay? There's more to it than I can explain in these 5 minutes. All right, so 28, that is talking about a light-emitting diode, LED, and a diode only has 2 terminals. That's why it's called a diode. Okay, it's a PN junction, P-type semiconductor, N-type, right? You know that in an N-type semiconductor, the majority carriers are electrons. In a P-type, the majority carriers are holes. You know all that? And you should also know that electrons have a higher energy than the holes. So in a PN junction, that's the symbol of the PN junction. You see the arrow there shows the direction of current. And a PN junction can be forward biased or reverse biased. What's the difference? If you make P, the arrow is the P, if you make P positive and N negative, it's forward biased. Why? Because that's when the current flows in that arrow direction. So when the PN junction is forward biased, a current begins to flow. Let me complete that circuit. So you see the positive is connected to P, the negative is connected to N. And now what happens is the electrons from the N side fall into the holes. So the electrons go this way. You know that electrons always flow opposite to the direction of current, don't you? So the electrons in the N region fall into the holes in the P region. And because the electrons have a higher energy, when they fall into the holes, the excess energy is emitted in the form of light. That's how an LED works. Okay? The electrons are at a higher energy. They fall into lower energy holes. The excess energy is emitted in the form of light. Let me also draw this graph to show you what I mean. That's the energy of the electron, the N region. This is the energy of the hole. And so you see that that's the energy difference that's given out as light. A little bit of it will also be given out as heat. So that's the working of a PN junction. So in this case, since you want it to emit a lot of light, of course, it should be heavily doped. That means the number of majority carriers must be high. So the answer is a heavily doped PN junction with a forward bias. Because if it's reverse biased, that means you connect these terminals opposite, there will be no current. That means there will be no combination to produce light. That makes sense? Okay. I think with that, I am done with this part 2. And hopefully you can, you will look at this and you will send me the comments. And so I know if I'm going too fast or if I need to give more ideas, more of the concepts, do write to me. But also remember that I'm taking a lot of time trying to help some people out, and I want to keep doing this. And I also want to give a full tutorial of CBSE physics after I'm done with this. That's my next endeavor. So could you kindly subscribe? More important than that, share it with as many friends as possible so that all of those students, particularly those students who do not have so much money to give away going for entrance coaching, could be helped, by using resources such as this. That's my desire. So please share it, tell all your friends, and I'm going to keep doing this depending on the number of views that I get, And like I said, I intend to make complete CBSE tutorials for physics, every chapter taken from your textbook, completely explained. So let me know your comments and suggestions. Like this video, please subscribe and share it. See you on part 3, maybe in a couple of days. Thank you.